Hello and welcome to Nighttime Science. Close your eyes, let your shoulders drop, let your jaw unhinge slightly, releasing the tension of the day. We are about to go on a very long, very quiet journey. We are leaving the noise of the earth behind. We are drifting up through the thin layer of our atmosphere past the silence of the moon and out into the deep velvet black of the cosmos. Tonight we will speak of the heaviest things in the universe. We will speak of the quietest places. We will speak of black holes. There is a comfort in the concept of a black hole. They are the ultimate resting place of matter. They are the points where the frenetic energy of the universe finally stops, where the complex equations of existence resolve into a single silent point. Over the next several hours, we will explore 100 facts about these mysterious objects. We will not rush. There is no need for speed here. The gravity of our subject matter demands a slow, deliberate pace. We will drift from one fact to the next, like a spacecraft coasting on a long, elliptical orbit. As we begin, imagine the darkness of space not as an empty void, but as a calm ocean. You are floating in this ocean. It is cool, still, and vast. And in the distance there are islands of gravity, places where the ocean drains away into the unknown. These are the black holes. They are not monsters, they are simply the inevitable result of gravity. The force that holds us to our beds taken to its absolute limit. Let us begin our count. Let us begin our descent into the dark. 1. The idea of a black hole is much older than you might think. We often associate these objects with the high-tech astrophysics of the 20th and 21st centuries with Einstein and Hawking. But the seed of the idea was planted in the quiet English countryside in the year 1783. It came from a man named John Michell. Michell was not a professional astronomer in the modern sense. He was a clergyman, a rector in the village of Thornhill. In the evenings, when the village was asleep, he would think about gravity and light. Isaac Newton had already shown that gravity was a force that pulled on matter. Michel asked a simple, sleepy question. Does gravity pull on light? If light is made of particles, as Newton thought, then a star should pull on the light it emits, just as the earth pulls on a stone thrown into the air. Michel imagined a star so massive with gravity so strong that the escape velocity required to leave its surface would be faster than the speed of light itself. He calculated that if a star had the same density as the sun but was 500 times larger in diameter, its light would fall back down onto it. He called these theoretical objects dark stars. Imagine that for a moment. A star that is burning bright, furious with fusion and heat, yet to the outside universe it is perfectly invisible. A ghost star, a hidden giant. 13 years later, in 1796, a French mathematician named Pierre-Simon Laplace independently came to the same conclusion. Laplace was a man of precision, known for his work on celestial mechanics, the clockwork of the solar system. In his book, The System of the World, he wrote a passage speculating about these heavy, invisible bodies. He imagined that the largest luminous bodies in the universe might be invisible to us. It is a calming thought that the universe might be full of massive, silent giants that we simply cannot see. However, in later editions of his book, Laplace removed this section. In the early 19th century, the wave theory of light became popular. If light was a wave, like a ripple on a pond, it was not clear how gravity could pull on it. Waves do not have mass in the same way a stone does. So the idea of the dark star fell into a long slumber. It was a mathematical curiosity that was tucked away in the dusty corners of physics, waiting for a new theory to wake it up. That new theory arrived in 1915 with Albert Einstein. But Einstein did not set out to find black holes. He was looking for a new way to describe gravity. He proposed general relativity. Instead of gravity being a force that pulls like a rope connecting the Earth and the Sun, Einstein described gravity as a curvature. Imagine a soft mattress. If you place a heavy bowling ball in the center, the mattress curves down. If you roll a marble nearby, it follows the curve. It looks like it is being pulled, but it is just following the shape of the mattress. Einstein said that mass tells space-time how to curve and space-time tells mass how to move. This was a revolution. It changed the universe from a rigid box into a flexible fluid fabric. And in this fluid fabric, the possibility of a bottomless pit emerged. If you put enough mass in a small enough space, the mattress doesn't just curve, it pinches off. It creates a deep, infinite well. This was the return of the dark star, but now it was not just trapping light, it was trapping space itself. 4. The first person to solve Einstein's complex equations and find this bottomless pit was Carl Schwarzschild. His story is one of tragic genius. It was 1916, World War I was raging. Schwarzschild was a German physicist and astronomer, but he was serving in the army on the Russian front. He was not in a quiet university office. He was in the middle of a war zone, surrounded by the noise of artillery and the cold of winter. Yet in his spare moments, amidst the mud and the chaos, he calculated. He found a solution to Einstein's field equations for a single spherical mass. He calculated the size a mass would need to be compressed to for its gravity to become inescapable. We now call this critical radius the Schwarzschild radius. For a mass like our Sun, the Schwarzschild radius is about 3 kilometers, or roughly 1.86 miles. If you could squash the entire Sun down to the size of a small village, it would become a black hole. Schwarzschild sent his paper to Einstein. Einstein was amazed that an exact solution could be found so quickly and so elegant in its math. Schwarzschild died shortly after from an illness contracted at the front, but his radius remains the defining boundary of every black hole in the cosmos. 5. For decades, most physicists did not believe black holes were real. They accepted the math, but they rejected the reality. They thought it was an artifact, a quirk of the numbers that would never happen in the messy, real universe. They called it the Schwarzschild singularity, and they treated it like a mistake. Even Einstein himself wrote a paper in 1939 trying to prove that stars could not collapse that far. He argued that the particles inside the star would spin faster and faster as they got closer, stabilizing the star before it could vanish from the universe. Einstein was comfortable with a universe that was orderly and static. The idea of a star disappearing, leaving behind a wound in space-time, was deeply unsettling to him. It is a reminder that even the greatest minds can struggle to accept the true, extreme nature of nature. The universe is often stranger and more dramatic than we are comfortable imagining. 6. The term black hole itself is relatively new. For a long time, these objects had clumsy names like collapsed stars or frozen stars. The Russian scientists called them collapsars. The term frozen star came from the fact that due to the warping of time, a collapsing star would appear to freeze just at the moment it crossed the Schwarzschild radius. To a distant observer, the light would dim and shift to red, and the motion would stop, frozen for eternity. But in 1967, the American physicist John Archibald Wheeler popularized the term black hole. He didn't invent it. It had been used in 1964 by a journalist named Anne Ewing. But Wheeler gave it scientific weight. He used it during a conference in New York. The name stuck immediately. It was perfect. It captured the mystery, the emptiness, and the finality of the object. A hole in space. Black not because it is a color, but because it is the absence of light. The name allowed scientists to talk about these objects not as mathematical errors, but as physical things, as real as planets or stars. 7. Let us talk about the concept of density. To make a black hole, you need extreme density. Density is how much matter is packed into a certain space. Water has a density of 1 gram per cubic centimeter. Iron is about 8 grams per cubic centimeter. The core of our sun is about 150 grams per cubic centimeter. But this is nothing compared to a black hole. To turn the Earth into a black hole, you would have to crush the entire planet, all the oceans, the mountains, the cities, the iron core, the atmosphere, down to the size of a marble, specifically a marble with a radius of about 9 millimeters. Imagine holding the entire Earth in the palm of your hand. That is the density we are talking about. At that level of compression, matter as we know it ceases to exist. There are no atoms, no electrons orbiting nuclei. There is only mass and gravity. It is a state of existence that is pure and simple, yet impossible for our minds to truly visualize. 8. Black holes are simple. This is known as the no-hair theorem. In the 1960s and 70s, physicists including Werner Israel, Brandon Carter, and Stephen Hawking proved that black holes are incredibly standardized. A star is complex. It has mountains of plasma, magnetic sunspots, different chemical compositions, varying temperatures, and turbulent convection zones. A planet is even more complex with weather, geology, and life. But once an object collapses into a black hole, it loses all of its features. It loses its hair. A black hole has only 3 properties that we can measure from the outside: mass, spin, and electric charge. That is it. If you throw a grand piano into a black hole, or a rock of the same mass, or a book of the same mass, the black hole changes in exactly the same way. It forgets what it ate. All the complexity of the matter, the shape, the color, the chemistry, is erased from the observable universe. It is the ultimate simplification. In a chaotic universe, black holes are objects of perfect simple order. 9. There are different weight classes of black holes. We categorize them by their mass. The most common type is the stellar mass black hole. These are the ones formed from the death of massive stars. They typically weigh between 5 and 100 times the mass of our sun. There are likely 100 million of these stellar mass black holes just in our own Milky Way galaxy. They are everywhere, silent and unseen, drifting through the spaces between the stars. Then there are the supermassive black holes. These are the giants. They weigh millions or even billions of times the mass of the sun. They sit in the centers of galaxies like spiders in the center of a web. And recently we have begun to find evidence for intermediate mass black holes, which are in the middle, thousands of times the mass of the sun. But regardless of their size, the physics is the same. The silence is the same. The darkness is the same. 10. Black holes are not vacuum cleaners. This is perhaps the most common misconception. We often imagine a black hole as a cosmic drain, sucking up everything in the universe. But gravity doesn't work that way. Gravity is determined by mass and distance. If we were to magically replace our sun with a black hole of exactly the same mass, the Earth would not get sucked in. The Earth would not even change its orbit. We would continue to circle the black hole exactly as we circle the sun today. The only difference is that the sky would go dark. The plants would die from the cold, not from being eaten. A black hole only becomes dangerous if you get very, very close to it, usually within a few times the Schwarzschild radius. Unless you cross that specific line, a black hole is just another heavy object in the sky, exerting a gravitational pull just like a star or a planet. You can orbit a black hole safely forever provided you keep your distance. It is a peaceful orbit circling a dark void held in place by the curvature of space. 11. To understand the black hole, we must understand the star. A star is a delicate balance. It is a battle between two great forces. On one side, there is gravity. Gravity wants to crush the star. It wants to pull every atom of gas inward toward the center. On the other side, there is pressure. This pressure comes from the nuclear fires burning in the star's core. Inside a star like our Sun, hydrogen atoms are smashing together to create helium. This process, nuclear fusion, releases an immense amount of energy. This energy pushes outward. It pushes against the crushing weight of gravity. For billions of years, these two forces are locked in a stalemate. Gravity pushes in, energy pushes out. The star remains stable, it shines, it gives life. But this balance cannot last forever. The fuel is finite, the hydrogen will run out. And when the fuel runs out, the fire dies down. And when the fire dies down, gravity wins. Gravity always wins in the end. It is the most patient force in the universe. 12. Stars have life cycles just as living things do. They are born in vast clouds of dust and gas. They live for millions or billions of years, and then they die. The fate of a star depends entirely on how heavy it is at birth. A small star, like a red dwarf, will burn its fuel slowly and quietly, eventually fading into a white dwarf. A medium star, like our Sun, will swell up into a red giant, shed its outer layers, and also retire as a white dwarf. A white dwarf is a dense object about the size of Earth, but it is not a black hole. It is supported by a quantum mechanical effect called electron degeneracy pressure. The electrons refuse to be squeezed any closer together. But for stars that are born with more than 8 times the mass of the Sun, the story is different. These massive stars burn hot and blue. They live fast and die young. They fuse hydrogen into helium, then helium into carbon, then neon, oxygen, silicon, building heavier and heavier elements in their cores, trying desperately to generate enough outward pressure to hold back the gravity. 13. The beginning of the end for a massive star is the production of iron. Iron is the ash of nuclear fusion. For all lighter elements, fusing them together releases energy. Fusing hydrogen creates energy. Fusing carbon creates energy. But iron is different. Iron is stubborn. To fuse iron into something heavier, you have to put energy in. You don't get any energy out. It costs the star energy to fuse iron. So when the star's core turns to iron, the engine stops. The outward pressure that has supported the star for millions of years suddenly vanishes. In a fraction of a second, literally less than a quarter of a second, the iron core, which is about the size of the Earth, collapses. It collapses under its own weight at 25% the speed of light. This is the iron catastrophe. The core shrinks from the size of Earth to the size of a city, about 20 kilometers across. 14. This sudden collapse creates a shock wave. The outer layers of the star, which are still rushing inward, hit the ultra-dense core and bounce off. This bounce, combined with a flood of particles called neutrinos, tears the rest of the star apart. This is a supernova. It is one of the most violent and bright events in the universe. For a few weeks, a single supernova can outshine an entire galaxy of 100 billion stars. It is a glorious, explosive death. But we are interested in what is left behind. In the center of the explosion, amidst the expanding cloud of gas and dust, lies the remnant of the core. If the star was heavy but not too heavy, the remnant becomes a neutron star. A neutron star is a city-sized ball of neutrons so dense that a teaspoon of it would weigh 1 billion tons. But if the remnant core is heavier than about 3 times the mass of the Sun, even the neutrons cannot stand the pressure. 15. There is a limit to how much weight nature can support. This limit was calculated by a young Indian physicist named Subramanian Chandrasekhar in 1930 on a steamship voyage from India to England. He calculated that a white dwarf star could not be heavier than 1.4 times the mass of the Sun. If it were, it would collapse. This is known as the Chandrasekhar limit. Later, physicists Oppenheimer and Volkoff calculated a similar limit for neutron stars, known as the Tolman-Oppenheimer-Volkoff limit. If the core remnant exceeds roughly 2 to 3 solar masses, there is no force in the known universe, not electron pressure, not neutron pressure, nothing that can stop the collapse. The neutrons are crushed into one another. The structure of matter fails. The collapse continues. It goes past the density of a nucleus. It keeps going. It shrinks to a point. And that is how a black hole is born. It is the victory of gravity over everything else. 16. Let us visualize this collapse. Imagine a sphere of matter. As it shrinks, the gravity on its surface gets stronger. If you were standing on the surface of this collapsing star, which is impossible, but let us imagine, you would feel heavier and heavier. As the star shrinks to half its size, your weight quadruples. As it shrinks again, your weight quadruples again. The escape velocity shoots up. Soon, the escape velocity hits 100,000 kilometers per second, then 200,000. The sky above you seems to close in, as the light from the surrounding universe is bent toward you. Finally, the star shrinks past the critical circumference. The escape velocity hits 299,792 kilometers per second, the speed of light. At that precise moment, the star vanishes from the observable universe. The last rays of light try to leave, but they are pulled back. The door shuts. The event horizon is formed. The star is still there, falling inward, but it has left our reality. 17. Not all black holes are born from explosions. There is a theory that some very massive stars might skip the supernova stage entirely. These are called failed supernovae. In these cases, the core collapses so quickly and the black hole forms so fast that it swallows the shock wave before it can blow the star apart. The entire star, millions of times the mass of the Earth, simply blinks out of existence. One moment there is a bright blue star. The next moment, darkness. Astronomers search for these vanishing stars by comparing photos of the sky taken years apart. They look for stars that were there in one photo and gone in the next, without any record of an explosion. It is a quiet, sudden death. A star that simply gives up the ghost and slips into the shadows without a sound. 18. When a black hole forms, it retains the angular momentum of the star that made it. Stars spin. Our sun spins once every 27 days. Massive stars spin much faster. When an ice skater pulls her arms in, she spins faster. This is the conservation of angular momentum. Now imagine a star that is millions of kilometers wide collapsing down to a point 20 kilometers wide. It spins up incredibly fast. Some black holes spin at thousands of times per second. This spin is crucial. It drags the fabric of space-time around with it, creating a vortex of gravity. A stationary black hole is a sphere, but a spinning black hole bulges at the middle. It creates a region called the ergosphere, where space itself is moving faster than light relative to the outside universe. We will explore this spinning dark carousel later, but for now, know that the death of a star is a frantic, spinning descent. 19. The material that is blown away in the supernova, the parts of the star that did not fall into the black hole, is vital for us. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of these were forged in the cores of massive stars and scattered by the explosion. We are made of stardust, but the black hole is the part of the star that we do not get back. It is the matter that is locked away. It is a cosmic vault. The universe recycles most of its material. New stars are born from the ashes of old ones, but the matter in a black hole is removed from this cycle. It is taken out of circulation. It is a one-way street. The formation of a black hole is the universe sequestering a piece of itself, hiding it away forever. 20. There is a profound stillness in the aftermath. The shockwave of the supernova expands outward, thinning over thousands of years into a beautiful nebula. These nebulae are often colorful, reds, greens, and blues, glowing with the energy of ionized gas. In the center of this colorful, expanding cloud, there is a dark spot, a spot where the background stars are blocked. This is the new black hole. It sits there, invisible, surrounded by the bright debris of its own birth. It is a tombstone for the star. Over time, the nebula will fade, the gas will drift away or form new stars. But the black hole will remain. It will wait. It will drift through the galaxy, dark and silent, potentially for trillions of years. It has all the time in the world. 21. We arrive now at the boundary, the defining feature of a black hole, the event horizon. It is a beautiful name for a terrifying concept. It is not a solid surface. You could not stand on it. It is a mathematical shell, a point in space where the rules change. It is the point of no return. Imagine a river flowing toward a waterfall. As you get closer to the edge, the water flows faster. If you are in a boat, you can paddle upstream and escape as long as you paddle faster than the current. But there is a point right at the lip of the falls where the water is flowing faster than you can paddle. Even if you paddle at your absolute maximum speed, you will still go backward. You will go over the edge. The event horizon is that point where space itself is flowing inward at the speed of light. Since nothing can travel faster than light, nothing can paddle upstream. Once you cross this line, there is no direction called out. All paths, all futures lead inward. 22. The size of the event horizon depends directly on the mass of the black hole. It is surprisingly small. For a black hole with the mass of our Sun, the event horizon would be a sphere only 6 kilometers, 3.7 miles across. You could fit it inside a medium-sized city. For a black hole with the mass of the Earth, the event horizon would be the size of a marble. For a supermassive black hole like the one in the center of the galaxy M87, which is 6.5 billion times the mass of the Sun, the event horizon is huge. It is about the size of our entire solar system. But regardless of the size, the nature of the boundary is the same. It is the edge of the observable universe. Anything that happens inside is forever disconnected from the outside. It is a private reality cut off from the rest of creation. 23. The event horizon acts like a one-way membrane. Information can go in, but it cannot come out. Light, radio waves, matter, heat, they all cross the boundary and vanish. To an observer on the outside, looking at a black hole is like looking at a perfectly black sphere. It reflects nothing. It emits nothing, if we ignore Hawking radiation for a moment, which is very faint. It is the blackest black in the universe. A black piece of paper still reflects some light. Vantablack, the darkest man-made material, absorbs 99.96% of light. A black hole absorbs 100%. It is a perfect absorber. It is a hole in the visual field, a silhouette against the stars. 24. Let us talk about light cones. In relativity, we use light cones to map out the future. Imagine a flash of light. It spreads out in a sphere. On a graph of time versus space, this expanding sphere looks like a cone growing upward. Inside the cone is your future, outside is inaccessible. Far away from a black hole, your light cone points straight up. You can move left, right, forward, backward. But as you get closer to the black hole, gravity tips your light cone over. It tips it toward the black hole. More and more of your possible future paths lead toward the dark star. At the event horizon, the light cone is tipped a full 90 degrees. The entire cone, every possible path your future can take, points inward. To move out would require moving backward in time, which is impossible. Space and time have swapped roles. Moving toward the center is as inevitable as moving toward tomorrow. You cannot stop it. 25. The event horizon is also a place of extreme silence. We are used to echoes. We shout, and the sound comes back. We shine a light and it reflects. But at the horizon, there are no echoes. If you were to lower a friend on a rope toward the horizon, a very strong rope, and they shouted to you, their voice would get deeper and slower. As they touched the horizon, their voice would stop. The light from their flashlight would dim to nothing. They would not disappear with a flash or a bang. They would simply fade. The last photon they emitted right at the edge would hover there, trying to escape but unable to make progress, suspended forever in a twilight state. It is a quiet departure. 26. There is a region just outside the event horizon called the photon sphere. This is usually at 1.5 times the Schwarzschild radius. In this region, gravity is so strong that light itself can orbit the black hole. Imagine shining a flashlight horizontally. The beam of light would circle the black hole and hit you in the back of the head. If you were standing in the photon sphere and you looked forward, you would see the back of your own head. You would see a ring of light that contains the images of the entire universe, bent and warped, circling endlessly. It is a hall of mirrors created by gravity. Orbits here are unstable, though. If a photon wobbles just a tiny bit, it will either spiral into the hole or escape to infinity. So the photon sphere is a fleeting razor-edge place, a thin shell of trapped light. 27. The shape of the event horizon must be a sphere for a non-spinning black hole. Gravity pulls equally in all directions. It does not make cubes or pyramids, it makes spheres. It is the most efficient shape in nature. It minimizes the surface area for a given volume. The event horizon is the most perfect sphere in the universe. Planets have mountains and valleys. They bulge at the equator. Even neutron stars have mountains a few millimeters high. But the event horizon is defined by math. It is smooth. It is featureless. It is geometrically perfect. 28. Despite its name, the horizon is not a physical barrier. If you were falling into a supermassive black hole, you would not hit the horizon. You wouldn't crash into a wall. You wouldn't hear a warning siren. You would simply float through it. The view around you might change. The darkness might encompass more of your vision. But locally, right where you are, nothing dramatic happens at that exact second. This is the equivalence principle of Einstein. Free fall feels like floating, whether you are falling toward the Earth or toward a singularity. It is only later, when you try to send a message back home, that you realize the phone line is dead. You have crossed the line without even feeling a bump. 29. The area of the event horizon is related to the concept of entropy. In the early 1970s, Jacob Bekenstein proposed that the surface area of the event horizon is a measure of the black hole's entropy, the amount of disorder or hidden information it contains. This was a radical idea. It suggested a link between gravity, quantum mechanics, and thermodynamics. Stephen Hawking initially disagreed, but later confirmed it with his famous calculation of Hawking radiation. The formula for the entropy of a black hole is carved onto Hawking's tombstone in Westminster Abbey. It essentially says that the amount of information a black hole can hold is proportional to its surface area, not its volume. This has led to the holographic principle, the idea that the entire 3D universe might be a projection of information stored on a 2D surface, much like the event horizon stores the information of the black hole. 30. The event horizon protects us. It is a cosmic sensor. Inside the horizon, at the singularity, the laws of physics break down. Infinite density, infinite curvature. If we could see this naked singularity, it might destroy our understanding of the universe. It might unleash unpredictability. But the event horizon wraps around the singularity, cloaking it from view. It hides the breakdown of physics. Roger Penrose coined this the cosmic censorship hypothesis. It suggests that the universe forbids naked singularities. It ensures that whenever a singularity forms, An event horizon forms around it, keeping the chaos contained. We are safe on the outside, allowed to keep our laws of physics while the black hole keeps its secrets in the dark. 31. We must now address the relationship between gravity and time. In our daily lives, we perceive time as a constant. A second is a second. A minute is a minute. It ticks forward at the same steady rate for everyone, everywhere. But this is an illusion caused by living in a place with very weak gravity. Albert Einstein taught us that time is not rigid, it is flexible. It is a dimension, woven together with space into a four-dimensional fabric called space-time. Gravity is the warping of this fabric, and just as gravity stretches space, it also stretches time. The stronger the gravity, the slower time moves. This is not a mechanical error in our clocks. It is a fundamental property of the universe. Time itself flows more sluggishly near a massive object. Near a black hole, this effect becomes extreme. It is the ultimate slow-motion camera. If you could stand near a black hole, you would be wrapped in a blanket of slow time, while the rest of the universe rushed hurriedly ahead without you. 32. To understand the scale of this time dilation, we can look at our own Earth. Gravity here is relatively weak, but it still affects time. The clocks on the GPS satellites orbiting the Earth tick slightly faster than the clocks on the ground. They are farther away from the Earth's mass, so they experience less gravity, and therefore their time flows faster. The difference is only about 38 microseconds per day. It is a tiny amount, but if engineers did not correct for it, your GPS navigation would drift by kilometers every day. Now scale this up. A black hole is billions of times denser than Earth. Near the event horizon, the time dilation is not measured in microseconds. It is measured in years, centuries, and eons. A minute spent hovering just above the horizon could equate to 1,000 years passing on Earth. You are not just traveling through space, you are traveling through time, held in a gravitational stasis while history unfolds rapidly in the distance. 33. This stretching of time affects light. As light tries to climb out of a gravity well, it has to work against the pull of the black hole. It loses energy. For a particle of light, a photon, losing energy does not mean slowing down. Light always travels at the speed of light. Instead, losing energy means changing color. The light wave gets stretched out. The distance between the peaks of the wave gets longer. This shifts the light toward the red end of the electromagnetic spectrum. This is called gravitational redshift. If you were to shine a blue flashlight from near a black hole up toward a friend in a spaceship, they would not see blue light. They would see red light. If you moved closer, the light would stretch into the infrared, closer still into radio waves. This is the exhaustion of light, struggling to escape the heavy hand of gravity, fading into a low, long hum as it climbs into the void. 34. Let us return to the image of the frozen star. We touched on this earlier, but the visual implication is profound. Imagine you are watching a probe fall into a black hole. You are safe in a spaceship far away. As the probe approaches the event horizon, you see it slow down. The signals it sends back come slower and slower. The light from the probe turns red, then deep red, then infrared. But the most haunting thing is that you never actually see the probe cross the line. From your perspective, it appears to slow down until it stops completely, frozen just a hair's breadth above the horizon. Its image remains there, growing dimmer and redder, fading effectively to black, but never truly disappearing. It is a ghostly afterimage plastered onto the sky, preserved by the warping of time. The probe has crossed over long ago in its own timeline, but the news of its crossing can never reach you. It is suspended in your reality forever. 35. Now flip the perspective. Imagine you are the one falling in. Do you see the universe freeze? No. You see the universe speed up, but not infinitely. There is a common misconception that if you fall into a black hole, you will see the entire future of the universe flash before your eyes in an instant. This is not quite true. While time is passing faster outside, the light from that future has to catch up to you, and you are falling away from the light at nearly the speed of light. However, the view is still spectacular. The light from the stars above you gets shifted the opposite way. It gets blue shifted. It gains energy as it falls in with you. The starlight becomes intense, energetic, and concentrated. For a brief moment, you are bathed in the accelerated light of the galaxy, a rain of high-energy photons pouring down into the abyss with you. 36. This brings us to the famous twin paradox, taken to its logical extreme. If you have identical twins and one stays on Earth while the other travels to a black hole, their ages will diverge drastically. The twin who travels to the black hole and orbits just outside the event horizon for a few weeks will return to Earth to find that their sibling has been dead for centuries. Entire civilizations may have risen and fallen. The landscape of the Earth may have changed. The language spoken may be unrecognizable. This is a lonely form of time travel. It is a one-way trip into the future. Gravity acts as a preservative, keeping the traveler young while the rest of the cosmos ages and withers. There is a melancholy in this physics. The realization that to explore the deep gravity of the universe is to sever your ties with your own time. 37. At the very center of the black hole, at the singularity, our understanding of time breaks down completely. In our world, time always moves forward. You cannot stop it, you cannot go back. But inside a black hole, the roles of space and time swap. The radial direction, the path toward the center, becomes your time. You can no more stop moving toward the center than you can stop moving toward next Tuesday. The singularity is not a place in space. It is a moment in your future. It is a point in time that you will inevitably reach. And once you reach it, calculations suggest that time itself ends. The timeline terminates. There is no after. It is the final period at the end of the sentence of existence. 38. There is another effect called frame dragging, or the lens-thirring effect. If the black hole is spinning, it drags space-time along with it like a spoon stirring honey. Space itself begins to rotate. If you were floating near a spinning black hole, you would find yourself being dragged sideways, orbiting the hole, even if you had engines trying to keep you still. You are not moving through space. Space is moving you. This twisting of the fabric creates a vortex. It is a whirlpool of time and geometry. Near the center, this twisting is so violent that it becomes impossible to stand still relative to the rest of the universe. To exist, there is to be spun, to be caught in the great rotation of the dark star. 39. Orbits around a black hole are not like orbits around a planet. Around a planet, you can orbit at any distance if you go the right speed. But around a black hole, there is a limit. It is called the innermost stable circular orbit, or ISCO. It is usually located at 3 times the Schwarzschild radius for a non-spinning black hole. If you try to orbit any closer than this, the orbit becomes unstable. Even the tiniest nudge, a stray atom, a photon, will cause you to spiral inward. You cannot correct it. You will drift inevitably toward the horizon. It is the edge of safety, the last stable foothold before the plunge. It creates a clear gap between the accretion disk and the black hole itself, a dark region where matter is falling freely, silent, and doomed. 40. The psychological implication of time dilation is one of eternal patience. From the perspective of the black hole itself, if it could have a perspective, the universe outside is buzzing like a fast-forwarded tape. Stars are born and die in moments. Galaxies spin like tops. The black hole sits in a bubble of slow time, watching the cosmos age and fade. It is the ultimate observer enduring while the lights of the universe burn themselves out. It is a reminder that time is relative, that urgency is an illusion of our biology, and that in the deep gravity of the dark, there is only the long, slow wait. 41. We move now to the physical experience of approaching the void. The first thing you would notice is the tidal force. Gravity gets stronger as you get closer to the source. This means that if you fall feet first toward a black hole, the gravity pulling on your feet is stronger than the gravity pulling on your head. Your feet are slightly closer to the center. On Earth, this difference is microscopic and imperceptible, but near a black hole, the gradient of gravity is steep. The difference becomes immense. You would feel a stretching sensation. Your body would be pulled straight, your spine elongated. It begins as a gentle traction, a relieving stretch, but it quickly becomes the dominant force in your world. 42. This process has a specific scientific name, and it is perhaps the most vivid term in all of physics: spaghettification. As the tidal forces increase, the human body or any object is stretched vertically and compressed horizontally. You are drawn into a long, thin strand. The structural integrity of your bones and tissues would eventually fail. You would not be crushed. You would be unraveled. You would become a stream of atoms, a long noodle of biological matter lining up single file to enter the horizon. It is a destructive process, yes, but there is a strange order to it. Gravity is trying to fit you into a space that is infinitely small, and to do so, it must reshape you into a line. 43. Counterintuitively, smaller black holes are more dangerous than larger ones. If you fall into a stellar mass black hole, one that weighs 10 times the sun, the tidal forces are horrific. The event horizon is small, only about 60 kilometers across. The gravity gradient is so steep that you would be spaghettified hundreds of kilometers before you even reached the event horizon. You would be dead long before you entered the black hole. The small black holes are violent, shredding anything that gets too close. They are surrounded by a zone of lethal tidal stress that acts as a grinder for matter. 44. However, for a supermassive black hole, the story is different. Let's look at the monster in M87 again. Its event horizon is the size of the solar system. Because it is so huge, the slope of gravity is much gentler. The distance from the center to the horizon is vast. If you fell into a supermassive black hole, the tidal forces at the horizon would be negligible. You would not be stretched. You would not feel pain. You would simply float across the line. You could check your watch, look around, and feel perfectly normal. You would be inside the black hole, trapped forever, but physically intact. You could live out the rest of your natural life inside the black hole, drifting toward the distant singularity, completely unaware that you have left the known universe behind. 45. When a star wanders too close to a black hole, it experiences a tidal disruption event, or TDE. The gravity of the black hole overcomes the gravity holding the star together. The star is torn apart. It is unraveled, just like the spaghettified astronaut. Roughly half of the star's gas is flung out into space while the other half falls inward. As this gas falls, it spirals and crashes into itself. It heats up to millions of degrees. It releases a scream of X-rays. Astronomers can see these events from billions of light years away. It is a sudden flare in a quiet galaxy, a signal that a sleeper has awakened to feed. 46. The gas from a disrupted star does not fall straight in. It wraps around the black hole. Imagine a stream of fluid pouring onto a sphere. It swings around, colliding with the tail of the stream. This creates a ring of debris. It is a chaotic, turbulent environment. The gas is moving at a significant fraction of the speed of light. The sheer kinetic energy involved is mind-boggling. A single star being eaten releases more energy in a few months than our sun will release in its entire 10 billion-year lifetime. It is a messy, inefficient feast. The black hole is a messy eater, spilling radiation and light out into the cosmos as it consumes matter. 47. The heat generated during this infall is due to friction. We usually think of space as cold and frictionless, but the gas density near a black hole is high. As the gas spirals in, layers of gas rub against each other. They are moving at different speeds, the inner layers moving faster than the outer layers. This shear force creates friction. Friction creates heat. The gas glows white hot, then blue hot, then X-ray hot. This is why black holes, despite being black, are often the brightest objects in the universe. We don't see the hole. We see the hot, glowing material screaming as it swirls down the drain. 48. Could a solid object survive? If you threw a steel bar into a black hole, would it stay a bar? For a small black hole, no. The tidal forces would snap the steel like a twig. The atomic bonds that hold iron atoms together are strong, but gravity is relentless. It would overcome the electromagnetic force binding the atoms. The steel bar would turn into a stream of iron vapor. For a supermassive black hole, the bar might survive the crossing, but eventually, as it approached the singularity deeper inside, the tidal forces would rise. Nothing rigid can maintain its shape against the infinite curvature of the center. In the end, everything becomes fluid, and then everything becomes geometry. 49. What would you see as you fell in? Imagine you are back floating, looking up at the sky. The black hole is beneath you. As you fall, the darkness below expands. It eats the stars. The circle of blackness grows larger and larger. But something strange happens due to the bending of light. The darkness doesn't just fill the bottom of your vision. It wraps up around the sides. It starts to feel like you are inside a bowl. Eventually, the blackness closes in from all sides, leaving only a small circle of starlight directly above you. This circle shrinks and shrinks, changing color until it is just a tiny dot of light. Then even that vanishes. You are enveloped in total, absolute isolation. 50. There is a final somber comfort in the lethality of the singularity. If you were to reach the point where spaghettification occurs, the process happens faster than the speed of nerve impulses. The human nervous system communicates pain at a finite speed. The physical disintegration of the body at the quantum level would occur in a time frame smaller than the brain's ability to process a signal. There is no biological capacity to experience the final moment. It is a cessation of existence that is faster than thought, faster than sensation. One moment you are, the next you are part of the curvature. It is a seamless transition from biology to physics. 51. At the heart of every black hole lies the singularity. It is the destination of all infalling matter. In the context of general relativity, the singularity is a point of zero volume and infinite density. It is where the mass of the star has been crushed down to literally nothing, yet retains all its weight. This concept of infinite density is a sign that our math has broken down. In physics, infinities are usually considered errors. They tell us that we are missing a piece of the puzzle, likely the effects of quantum mechanics. But until we have a theory of quantum gravity, the singularity remains a mystery. It is a tear in the fabric of reality, a place where the rules of the universe no longer apply. 52. However, most black holes are spinning. And for a spinning black hole, the singularity is not a point. It is a ring. This is known as a ring singularity or ringularity. The centrifugal force of the spin prevents the matter from collapsing all the way to a single point. Instead, it forms a ring of zero thickness but a finite radius. This ring sits flat in the center of the black hole. If you were falling into a spinning black hole and you maneuvered carefully, you could theoretically fall through the center of the ring without touching the singularity itself. Some theoretical solutions suggest this could be a gateway to a wormhole or a bridge to another universe, though this remains purely in the realm of mathematical speculation. 53. Surrounding the event horizon of a spinning black hole is a region called the ergosphere. The name comes from the Greek word ergon, meaning work. The ergosphere is an ellipsoidal region. It bulges out at the equator and touches the horizon at the poles. Inside the ergosphere, space-time is being dragged around faster than the speed of light. It is impossible to stand still here. Even if you had infinite rockets, you would still be dragged along with the rotation of the black hole. However, you are not yet inside the event horizon. You can still escape the ergosphere. It is a purgatory between the safe outer space and the inevitable inner void. 54. Because you can enter and leave the ergosphere, it is theoretically possible to steal energy from a black hole. This is called the Penrose process, named after physicist Roger Penrose. Imagine sending a spaceship into the ergosphere. The ship fires a projectile into the black hole against the direction of the spin. The recoil kicks the spaceship forward. Due to the weird physics of the ergosphere, the spaceship can emerge with more energy than it entered with. The energy comes from the rotation of the black hole. The black hole slows down slightly. A sufficiently advanced civilization could build a city around a black hole and use it as a battery, harvesting the energy of its spin for billions of years. 55. Most black holes are not naked. They are dressed in an accretion disk. This is a flat, rotating disk of gas, dust, and debris that is waiting to fall in. It looks like the rings of Saturn, but glowing with intense heat. The material in the disk is orbiting at tremendous speeds. The closer to the hole, the faster it moves. This differential rotation causes the friction we spoke of earlier. The accretion disk is the visible footprint of the invisible giant. It is a swirling, glowing whirlpool that traces the gravitational contours of the beast. 56. The temperature of the accretion disk is not uniform. The outer edges might be relatively cool, perhaps a few thousand degrees, glowing red or orange, but as you move inward, the temperature skyrockets. Near the center, the gas is millions of degrees. It emits ultraviolet light and X-rays. This is why X-ray telescopes are our best tools for finding black holes. We look for points in the sky that are dark in visible light but blindingly bright in X-rays. Cygnus X1, the first black hole ever confirmed, was found this way. It is a star being eaten by a companion, the gas screaming in X-rays as it spirals to its doom. 57. The inner edge of the accretion disk is defined by the innermost stable circular orbit, ISCO. Inside this line, the gas cannot orbit. It plunges. This creates a gap between the bright disk and the black hole itself. This gap is the plunging region. The material here is falling freely, accelerating toward the speed of light. Because the gas becomes thinner as it falls, and because the light it emits is strongly redshifted by gravity, this region appears dark. It creates the shadow of the black hole, a dark circle silhouetted against the bright ring of the disk. This shadow is what the Event Horizon Telescope captured in its famous image of M87 Tau. 58. Black holes are often surrounded by intense magnetic fields. The charged particles in the accretion disk, whirling around at near light speed, create a dynamo effect. These magnetic fields are incredibly powerful. They can be millions of times stronger than the Earth's magnetic field. The field lines get twisted and tangled by the spin of the black hole and the motion of the disk. They act like giant invisible rubber bands, snapping and reorganizing, channeling the plasma and directing the flow of energy. 59. This leads to the phenomenon of relativistic jets. In some black holes, not all the matter falls in. A small fraction of the material is caught by the magnetic fields before it reaches the horizon. It is funneled toward the poles, the north and south axis of the spin. There it is blasted outward into space at 99.9% the speed of light. These jets can extend for thousands of light years, piercing through the galaxy and out into intergalactic space. They are like cosmic blowtorches. We see them as straight lines of fire shooting from the darkness. They redistribute matter and energy, acting as the ventilation system for the galaxy. 60. The black hole is not an isolated object. It interacts with its environment. This is called feedback. The energy from the jets and the radiation from the accretion disk can heat up the surrounding gas in the galaxy. This heat can prevent the gas from cooling down to form new stars. In this way, a black hole can control the fate of its entire host galaxy. It can shut down star formation. It can keep the galaxy red and dead, filled with old stars but no new ones. The tiny black dot in the center, smaller than a solar system, dictates the life and history of the massive galaxy around it. It is a ruler that governs through gravity and fire. 61. We must now speak of the giants, the supermassive black holes. These are not just large versions of stellar black holes. They are a different class of entity entirely. They range from hundreds of thousands to billions of solar masses. While a stellar black hole is the corpse of a star, a supermassive black hole is the anchor of a galaxy. Almost every large galaxy in the universe, including our own Milky Way, has a supermassive black hole at its center. They are the standard equipment of galactic architecture. The question of how they formed is one of the great open mysteries of cosmology. Did they start small and grow? Or were they born huge in the early universe? 62. Our own supermassive black hole is named Sagittarius A, pronounced A star. It sits in the direction of the constellation Sagittarius. It is relatively quiet and small compared to others, weighing about 4 million times the mass of our Sun. It is 26,000 light-years away from us. We are safe from it. It is currently on a starvation diet, consuming only wisps of gas and the occasional asteroid. Because it is not eating much, it is not very bright. It sleeps in the center of the Milky Way, a dormant volcano of gravity holding the galaxy together not by its pull, which is negligible at this distance, but by its role in our history. 63. How do we know Sagittarius A is there if it is dark? We watch the stars around it. There is a group of stars called the S stars that orbit a blank spot in space near the galactic center. One star, S2, completes an orbit every 16 years. It whips around the empty point at speeds of up to 5,000 kilometers per second. By tracing the orbits of these stars, we can use Kepler's laws to calculate the mass of the object they are orbiting. The only thing that can be that heavy, 4 million suns, and that's small, fitting inside the orbit of Mercury, is a supermassive black hole. Watching these stars is like watching leaves swirl in a gust of wind. You can't see the wind, but the movement of the leaves reveals its power. 64. The largest black hole we have measured with high precision is TON 618. It is a behemoth. It is an ultramassive black hole. It weighs 66 billion times the mass of the Sun. 66 billion. It is hard to comprehend such a number. If you place TON 618 in the center of our solar system, its event horizon would extend far beyond the orbit of Pluto, beyond the Kuiper belt, and deep into interstellar space. A beam of light would take weeks to cross its diameter. It shines as a quasar, brighter than 140 trillion suns. It is a relic from a different time, a monster that grew fat on the rich gas of the early universe. 65. There is a remarkable correlation known as the M-sigma relation. It shows that the mass of the supermassive black hole is tightly linked to the mass of the galaxy's central bulge of stars. The black hole is almost always about 1,000th of the mass of the bulge. This implies that the black hole and the galaxy grow together. They are symbiotic. One does not simply live inside the other, they evolve in lockstep. The growth of the black hole regulates the growth of the galaxy, and the galaxy feeds the black hole. They are partners in a cosmic dance that spans billions of years. 66. When the universe was young, these supermassive black holes were much more active. We call them quasars, quasi-stellar radio sources. A quasar is simply a supermassive black hole that is eating voraciously. It has a massive accretion disk that outshines the entire galaxy hosting it. When we look at a quasar, we are looking back in time to when the universe was only 2 or 3 billion years old. We see them as bright beacons in the dark ages. They are the lighthouses of the deep past, showing us where the matter was congregating when the cosmos was still under construction. 67. There is a limit to how fast a black hole can grow. It is called the Eddington limit. As matter falls in, it heats up and radiates light. This light exerts outward pressure. If the black hole tries to eat too fast, the light pressure blows the food away. It chokes on its own meal. This limit restricts how quickly a black hole can gain mass. However, some black holes in the early universe seem to have broken this rule. They are too big, too early. This suggests they might have formed from the direct collapse of massive gas clouds, bypassing the star stage entirely, or that they have a way of force-feeding themselves above the theoretical limit. 68. Galaxy mergers are the great feasts for supermassive black holes. When two galaxies collide, their central black holes eventually find each other. They sink to the center of the newly combined galaxy. As they spiral toward each other, their gravity disrupts the gas in the galaxy, funneling vast amounts of it into their maws. This triggers a dual quasar phase where two active black holes blaze side by side. Eventually, they will merge into one larger black hole, sending a tsunami of gravitational waves through the universe. 69. We have found wandering black holes. Sometimes in a galaxy merger, one black hole can be kicked out. If the gravitational waves from the merger are emitted asymmetrically, they can give the new black hole a kick, a recoil effect. This kick can be strong enough to eject the black hole from the galaxy entirely. These rogue, supermassive black holes roam the intergalactic void, untethered, dragging a small cluster of stars with them like an entourage. They are lonely kings without a kingdom, drifting in the vast emptiness between the islands of light. 70. The influence of a supermassive black hole extends far beyond its gravitational reach. Through its jets, it injects energy into the intra-cluster medium, the hot gas that fills the space between galaxies in a cluster. These jets blow bubbles in the gas, cavities that are millions of light years wide. These are the largest structures created by a single object in the universe. The black hole acts as a heating element, keeping the gas in the cluster hot and preventing it from cooling down to form stars. It is a mechanism of cosmic climate control, regulating the temperature of the universe on the largest scales. 71. How do we take a picture of something that is by definition invisible? This was the challenge facing the Event Horizon Telescope, EHT team. A black hole absorbs all light. You cannot photograph it directly. Instead, you must photograph the silhouette it casts against the glowing gas behind it. It is like trying to photograph a black cat in a coal cellar, but the cat is wrapped in glowing fairy lights. The picture of a black hole is really a picture of the absence of light in the center of a ring of fire. This shadow is the closest we can get to seeing the face of the void. 72. To see the black hole in M87, which is 55 million light-years away, we needed a telescope the size of the Earth. Obviously, we cannot build a dish that big. So scientists used a technique called Very Long Baseline Interferometry, VLBI. They took radio telescopes located in Hawaii, Arizona, Mexico, Spain, Chile, and the South Pole, and synchronized them using atomic clocks. By recording the data simultaneously and combining it, they created a virtual telescope with the resolution of an Earth-sized dish. This resolution is high enough to read a newspaper in New York while standing in Paris. 73. The data recorded by these telescopes was so vast it could not be sent over the internet. It was measured in petabytes. The hard drives had to be physically flown to central processing centers in Germany and the United States. They were flown on airplanes. This is colloquially known as sneaker net. It was faster to fly boxes of hard drives across the ocean than to transmit the data via fiber optics. The physical weight of the data was hundreds of kilograms. The black hole's image was literally carried in suitcases through international airports. 74. The famous image of M87 SEC released in April 2019 shows a blurry orange donut with a dark center. The orange color is a choice by scientists. Radio waves have no visible color. They chose orange to represent the intensity of the emission, the heat. The bright part of the ring is brighter because of the Doppler beaming effect. The gas on that side is moving toward us, making it appear brighter and more energetic. The dark central patch is the shadow of the black hole. It is about 2.5 times larger than the event horizon itself due to the way gravity bends the light around the sphere. It is a portal into the unknown, captured on a hard drive. 75. Albert Einstein, if he were alive, would have been pleased but likely unsettled by the image. The shape of the shadow matched the predictions of general relativity perfectly. The theory held up even in the most extreme environment in the universe. There were no deviations, no cracks in the theory. Gravity behaves exactly as the math says it should, right down to the edge of the abyss. It is a testament to the power of human thought that a man writing equations in Berlin in 1915 could predict the shape of a shadow in a galaxy 55 million light-years away. 76. Gravitational lensing is another way we see black holes. Because a black hole has such intense gravity, it acts like a lens. It bends light. If a black hole passes in front of a distant star, the star's light will be magnified and distorted. It might appear as a bright ring, an Einstein ring. Or it might split into 4 distinct images, forming an Einstein cross. Astronomers look for these distortions to find black holes that are otherwise invisible. It is like looking through the bottom of a wine glass. The background is warped, revealing the presence of the glass. 77. The photon ring is a theoretical feature that we hope to see with future, sharper telescopes. Inside the blurry donut of the M87 image, there should be a thin, razor-sharp ring of light. This ring is composed of photons that have orbited the black hole multiple times before escaping. It is a history record. The light in the photon ring has made several laps, gathering information about the black hole from different angles. Seeing this subring would be the ultimate test of gravity, allowing us to measure the spin and mass with perfect accuracy. 78. Visualizing a black hole in 3D is a challenge for the mind. We see the 2D image of the disk, but in reality the light is coming from all around the object. The accretion disk might be flat, but the gravity bends the light from the back of the disk up and over the top and down and under the bottom. So when you look at a black hole, you see the top of the disk, the bottom of the disk, and the back of the disk all at once, framing the black sphere. It is a visual paradox, a geometry that defies our Euclidean intuition. 79. Computer simulations play a huge role in our understanding. Before we had the EHT image, we had simulations. The most famous one was created for the movie Interstellar. Physicist Kip Thorne worked with visual effects artists to solve the equations of light propagation around a spinning black hole. The result, the black hole Gargantua, was hailed as one of the most scientifically accurate depictions ever made. It showed the glowing disk, the bending of light, and the strange asymmetry caused by the spin. It allowed millions of people to visualize the beauty of the void. 80. There is a soothing quality to the image of the black hole shadow. It is a perfect circle of darkness. In a universe filled with chaotic shapes, irregular nebulae, spiral galaxies, jagged asteroids, the black hole is an object of pure geometry. It is the eye of the storm. It is the still point of the turning world. To look at it is to look at the limit of our knowledge, the edge of the map. It is the ultimate mystery sitting there quietly defying us to understand it. 81. For centuries we studied the universe only through light. Visible light, radio waves, X-rays, all form part of the electromagnetic spectrum. But black holes by their nature are dark. To truly study them we needed a new sense. We needed to be able to hear gravity. In 2015 we gained this sense. We detected gravitational waves. These are ripples in the fabric of space-time itself. When massive objects move, they create waves, just as a ship creates a wake in the water. These waves travel at the speed of light, squeezing and stretching space as they pass. They pass through the Earth, through you, through everything, silent and invisible. 82. The instrument that detected them is LIGO, the Laser Interferometer Gravitational Wave Observatory. It is a marvel of precision. It consists of 2 tunnels, each 4 kilometers long, arranged in an L shape. A laser beam is split and sent down both tunnels, bouncing off mirrors. If a gravitational wave passes, it stretches one tunnel and squeezes the other by a tiny fraction. How tiny? Less than the width of a proton. LIGO detects this microscopic shift. It is like measuring the distance to the nearest star to within the width of a human hair. It is the most sensitive ruler ever created. 83. The first signal detected, GW1FEMVO914, came from the collision of 2 black holes. They had been orbiting each other for millions of years. As they circled, they emitted gravitational waves, losing energy. They spiraled closer and closer, faster and faster. In the final fraction of a second, they were spinning around each other hundreds of times per second. Their event horizons touched. They merged. The energy released in that final moment was greater than the light of all the stars in the observable universe combined, but it was released in darkness, as pure gravitational vibration. 84. This signal is often called a chirp. If we translate the frequency of the gravitational waves into sound, it sounds like a bird chirping. It starts low and slow, whoop, and then rapidly pitches up, whoop, whoop, before cutting off abruptly. The cutoff happens at the moment of merger, when the 2 holes become one and the ringing stops. This chirp is the swan song of the 2 black holes. It is the sound of space-time screaming under the stress of the collision. We have heard this sound dozens of times now from all corners of the sky. The universe is full of these chirps, a choir of merging shadows. 85. When 2 black holes merge, the new black hole is lighter than the sum of the original 2. Where did the mass go? It was converted directly into energy, the energy of the gravitational waves. Il a $. In the first detection, 3 solar masses, 3 times the mass of our entire sun, were converted into pure energy in less than 1/10 of a second. This is the most efficient energy conversion process known in the universe. It dwarfs nuclear fusion. It is the ultimate release of potential energy. 86. Gravitational waves pass through everything. Light can be blocked by dust or planets, but gravitational waves travel unimpeded. They carry information from the deepest, densest, and darkest parts of the cosmos directly to us. They allow us to see inside the merger, to probe the dynamics of the event horizon itself. We are no longer limited to looking at the skin of the universe. We can feel its bones shifting. 87. The detection of these waves confirmed another prediction of Einstein, one he thought would never be verified. He thought the waves would be too weak to ever detect. He underestimated the violence of the universe and the ingenuity of his descendants. The fact that we can measure the stretching of space by a fraction of a proton is a testament to the quiet persistence of science. It took 40 years of development to build LIGO. It was a generational project, a long-term investment in listening to the dark. 88. We have also detected neutron star mergers. These are different. They produce light as well as gravitational waves. They are the kilonovae. These explosions forge the heavy elements: gold, platinum, uranium. The gold in your ring was likely created in the collision of two dead stars, a collision that sent ripples through space-time that we can now hear. It connects the rare metals of Earth to the violent history of the cosmos. 89. Future detectors like the space-based LISA, Laser Interferometer Space Antenna, will be able to detect supermassive black hole mergers. LISA will consist of 3 spacecraft flying millions of kilometers apart, firing lasers at each other. It will be sensitive to low-frequency waves, the deep, slow rumblings of the giants. It will allow us to hear the mergers of galaxies themselves. We will be able to map the history of black hole growth back to the dawn of time. 90. There is a stillness that follows the merger. After the violent ring-down phase, where the new misshapen black hole vibrates to settle into its final shape, silence returns. The waves propagate outward, fading into the distance. The new black hole, now larger and spinning faster, sits alone in the dark. It has consumed its partner. The ripples it created will travel forever, getting weaker and weaker, stretching the universe imperceptibly until the end of time. It is a permanent signature written on the fabric of reality. 91. For a long time, we believed that black holes were eternal. We thought that once a black hole formed, it could only grow. It could eat matter and get bigger, or it could sit there forever unchanged. We thought it was a perfect trap. But in 1974, the physicist Stephen Hawking changed everything. He applied the laws of quantum mechanics to the edge of the event horizon. He discovered something profound. He found that black holes are not truly black. They emit a faint glow. They radiate energy. This phenomenon is now known as Hawking radiation. It was a shock to the scientific community. It meant that black holes are not stable, permanent objects. They leak. They lose mass. Over incredibly long timescales, they are dying. It is a slow leak, a tiny drip of energy into the cold void, but it changes the ultimate fate of the universe. 92. To understand how a black hole can radiate, we must look at empty space. According to quantum field theory, a vacuum is not empty. It is seething with activity. Everywhere in the universe, pairs of virtual particles are constantly popping into existence. One is a particle, the other is an antiparticle. They appear, they exist for a fleeting fraction of a nanosecond, and then they crash back together and annihilate each other, vanishing. This happens everywhere, all the time. It is the quantum foam. Normally, these pairs cancel each other out so quickly that they have no effect on the macroscopic world. But at the event horizon of a black hole, something different happens. The horizon disrupts this cycle. 93. Imagine a pair of these virtual particles appearing right on the edge of the event horizon. One particle is just outside the line. The other is just inside. The particle on the inside is captured by gravity. It falls toward the singularity. It cannot return. The particle on the outside, however, is left without a partner. It cannot annihilate. It has become a real particle. To an observer far away, it looks like the black hole has just emitted a particle. But energy must be conserved. You cannot get something for nothing. The energy to make that particle real has to come from somewhere. It comes from the gravitational energy of the black hole itself. The particle that fell in effectively carries negative energy relative to the outside universe. It subtracts mass from the black hole. With every particle that escapes as Hawking radiation, the black hole gets a tiny bit lighter. 94. This process of evaporation is incredibly slow. It is inversely proportional to the mass of the black hole. This means that large black holes are very cold and evaporate very slowly, while small black holes are hot and evaporate quickly. For a black hole with the mass of our Sun, the temperature of this radiation is 1/10,000,000th of a Kelvin above absolute zero. It is practically nothing. It is far colder than the cosmic microwave background radiation, which fills all of space at 2.7 Kelvin. This means that right now, stellar mass black holes are actually gaining mass, not losing it. They are absorbing the background heat of the universe faster than they are radiating it away. They are colder than their environment, so they act as heat sinks. 95. However, the universe is expanding and cooling. In the far distant future, billions of years from now, the cosmic background radiation will fade. The universe will become colder than the black holes. When that happens, the flow of heat will reverse. The black holes will begin to lose mass faster than they gain it. They will start to shrink. But shrink implies a speed that is misleading. The time it takes for a supermassive black hole to evaporate is mind-boggling. It is estimated to be roughly 1 Google years. That is a 1 followed by 100 zeros. It is a timescale so vast that the current age of the universe, 13.8 billion years, is like a single blink of an eye in comparison. 96. As a black hole shrinks, it gets hotter. This is a strange feature of black hole thermodynamics. It has negative heat capacity. As it loses energy, its temperature goes up. A shrinking black hole emits radiation faster and faster. For most of its life, a black hole emits only long wavelength radio waves. But as it gets down to the size of a mountain, it starts to glow white hot. As it gets down to the size of an atom, it emits hard gamma rays. The final moments of a black hole's life are not quiet. After eons of silence, the black hole sheds its cloak of darkness and becomes a brilliant, explosive source of energy. 97. The death of a black hole is an explosion. When the mass becomes very small, the evaporation process runs away. The black hole dissipates its remaining mass in a fraction of a second. This final pop releases a burst of high-energy particles and gamma rays equivalent to the detonation of millions of nuclear bombs. It is a violent farewell. However, because the lifespan of black holes is so long, not a single black hole in the universe has evaporated yet. The universe is too young. We have not seen this happen. We are living in the early spring of the cosmos, long before the harvest of the black holes. 98. The evaporation of black holes leads to a deep problem in physics called the information paradox. In quantum mechanics, information is never destroyed. If you burn a book, the information is technically still there in the ash and the smoke. If you could collect every particle of ash and every photon of light, you could theoretically reconstruct the book. But if a book falls into a black hole and the black hole then evaporates into Hawking radiation, where did the information go? The radiation seems to be random heat. It does not seem to carry the details of the book. If the black hole disappears completely, the information seems to be erased from the universe. This violates the fundamental rules of quantum mechanics. Resolving this paradox, figuring out if the information is preserved in the radiation or destroyed, is one of the biggest goals of modern physics. 99. Let us look to the very end. The black hole era. Cosmologists divide the future of the universe into eras. We are currently in the stelliferous era, the era of stars. But stars will stop forming. The fuel will run out. The lights will go out. Roughly 100 trillion years from now, the last red dwarf star will die. The universe will become dark. The only heavy objects left will be black holes. They will be the kings of the ashes. They will drift through the dark, cold vacuum, occasionally swallowing a stray dead star, but mostly just slowly evaporating. This era will last for a length of time that is impossible to visualize. The universe will be a graveyard of gravity. And finally, after the Google years have passed, even the black holes will be gone. They will have all evaporated one by one, lighting up the dark for a brief moment before vanishing. What will be left? Only a sea of photons and light particles cooling toward absolute zero. The universe will reach a state of maximum entropy. It will be a state of perfect equilibrium. No more stars, no more planets, no more black holes, no more time. Just a vast, timeless, featureless soup of cold radiation. This is the heat death of the universe. It sounds sad, perhaps, but there is a peace in it. It is the ultimate rest. It is the end of all struggle, the end of all gravity, the end of all noise. It is the final, eternal sleep of the cosmos. We have reached the end of our count. We have traveled from the English countryside of the 18th century to the event horizon of M87. We have watched stars collapse into points of infinite density. We have felt the stretching of the tidal forces and the slowing of time. We have listened to the chirp of merging giants and watched the slow quantum evaporation of the last remnants of matter. The black hole is a paradox. It is an object of violence, born in fire and collapse. Yet it is also an object of profound silence and order. It is the simplest object in the universe, a pure expression of geometry and gravity. It is a place where the frenetic activity of the universe comes to a halt. As you lie there, let the concept of the black hole weigh on you, not as a scary thought, but as a grounding one. The universe is vast, and it creates these heavy anchors. They hold the galaxies together, they structure the cosmos. They are the silent guardians of the dark. There is no need to understand all the math tonight. There is no need to worry about the paradoxes or the singularities. Those are problems for another time, or perhaps for no time at all. For now, it is enough to know that they are there, drifting, spinning, waiting. The universe is a quiet place. The spaces between the stars are deep and calm. The black holes are the quietest places of all. Let your mind drift into that quiet. Let your thoughts spiral inward, slowing down as they approach the center, stretching out, relaxing until they freeze. Sleep is a kind of event horizon. It is a boundary we cross every night. We slip from the world of light and noise into a private, dark reality. We let go of the outside world. We let gravity take us. You are safe. The earth is holding you. The sun will rise tomorrow. The black holes are far away, doing their work in the deep dark. You can rest now. If you enjoyed this long drift through the cosmos, please leave a like and subscribe to join us for more nighttime science. Good night.